Green's theorem. So there are two applications, particularly in source signature and radiation patterns, separating the reflection data from the reference wave and the source and receiver below. We have application comes out the idea of many of these new ideas here. And then there's Wavefield prediction, which will be a separate set of talks. We talked about that new article. So what we're going to do is illustrate the idea here. As we said, we're interested in a math description that describes wave and what influences the wave. So what influences the wave will be, of course, the source, where it's located, say some spatially varying velocity. Just as an example, all this Green's theorem can be written elastic and in any kind of form you want. We're just illustrating it here. Acoustically, to give you the idea. And in the pages we've written, we've generalized it to more complicated, but there's no point in putting superscripts and subscripts here. So what we're going to do is we're going to take this velocity field and characterize it in terms of a reference velocity and this function alpha bar, which you'll see often here. This alpha bar, this is the definition of alpha bar. It then characterizes the difference between the actual velocity at a point and, in this case, a constant reference velocity. So what we do is then we rewrite this so that on this side there's a differential operator which cares only about reference properties, and then you have some terms on the right-hand side. We then look at these terms as source, as sort of driving terms. So the world here is then looked at in this view of waves and how waves are influenced. There is a world which is homogeneous, and in this case, and superimposed on it are sources that this is the energy source that creates the wave, and this is the source that makes at certain points in the medium the velocity different than C0. Do you want to stop and get some coffee? This is a lecture in insomnia. This is a cure for insomnia. If you have difficulty sleeping, this talk can solve that. That's one about delivery. If you need coffee, just while it's coffee, just go and get it. I'm going to keep going. That's I need. So you have this form. Now, there's a way, if you give me that the reference as C0, then you say, what do I have to superimpose on that homogeneous background, if you like, what source, then you can find the field everywhere, if you know the sources everywhere. And you get that by this corresponding equation, where the source is ideal, the Wavefield function, and then the solution to the problem on the last page, where the right-hand side is a function rho, is just a superposition of the solution for the Roth delta times the weight of the actual source at R prime. And so this is a solution. If you choose G0, you have to be causal. This means every point where there's a rho has an explosion with an outgoing wave in the homogeneous medium. And the weighted sum of those gives you the causal wave field for the actual wave in that equation on the previous page. It's a solution everywhere. If you give me all the influences explicitly in the world that a wave experiences, then you have a solution directly in terms of all those experiences. There's no boundary term, there's no initial term. If you give me the sources for all time and all space, in a form like this, you can write it in time as well. It gives you you'll see the role that boundary conditions play in solutions in a second. So that's one form. This is the wave solution anywhere in terms of the influences everywhere. There's a totally different description that comes from Isaac Newton, and which says that totally different. That last is sort of a very physical linearity, superposition, causality. This comes from mathematics. That fundamental theorem says that you have an integral. Amazing theorem. It says you can sum something in an interval and replace it by something else only on the endpoints, the antiderivative. That's the origin of this. This is the fundamental theorem of the integral calculus, but leads to the divergence theorem, which leads to this form of the divergence theorem, okay? Called Green's second identity, where at this stage, P and G0 are anything. It's just that you can make this psi and phi, okay? It doesn't matter, okay? It's just, so this, again, is amazing. There's an integral of something inside a volume, at every point in the volume, is replaceable by something else on the surface of the volume. Okay, so with that identity, if you substitute, if you specifically now in that equation call del square plus k square p is rho, and del square plus k square g0 is delta, meaning making something specific about what equations p and g0 satisfy, then you can derive from that Green's second identity this form for P for R in the volume, because right before this is an expression where it's P of R prime omega delta of R minus R prime. It asks the question, is R in the volume or not? If R is in the volume, you get this. If R is out of the volume, you get 0. So this plus this is 0 for R outside the volume. And for R in the volume gives you the field. This is discontinuous. The right-hand side is the field in the volume, and the instant you're outside is 0. What causes the discontinuity? This. This is discontinuous. The gradient. Why? Because the second derivative has to be like a Dirac delta. So it has to jump. It has to be heavy side. Yes? And that's what makes this thing change its mind, whether you're in or out. 0 or P. So, but for P in the volume, first of all, one of the amazing things, one of the joys of this job, okay, is teaching class math physics or seismic physics and never stopping to be amazed at what George Green and others have brought. That business before, P is integral rho G0 plus. Has to be G0 plus. If you want P to be causal, you got to add a causal weighted sum, weights. Here, to my amazement, even though I've done 1,000 times and 50 million examples, and our migration methods depend on what I'm about to say, any G0 that satisfies del square plus k squared G0 is delta in the volume, any, will make this be the causal solution in the volume. In other words, this can be causal, this can be anti-causal, as long as there's a surface term. As long as there is a surface term. Why? Because if you have P, and these values, P and the normal derivative of P, come from actual measurements, in other words, they're actual values of P and the normal derivative, they nail it down. It's like a boundary condition, yes? You're given information about the field. So, let me give it for instance. Let's say you happen to choose G0 minus, anti-causal. How in the world is a sum of anti-causal, anti-causal, anti-causal going to make that causal? That's so mind-boggling. If that wasn't true, all migration, one-way stope migration wouldn't work. It's using anti-causal. It's taking this wave that's up and with an anti-causal predicting it, yes? The reason, what this does in that case, this surface integral, you can show, will annihilate, produce the negative of rho G0 minus, and so it will produce minus, this surface integral will produce minus rho G0 minus, and it will produce rho G0 plus for this contribution due to the sources inside, plus this will give you the contribution due to all the sources outside. That's absolutely amazing. You can show that, we're not going to do that because we only have a few days here. We have a few years, we could do that. But it's mind-boggling, you understand? It's so counterintuitive. The sum of anti-causal things adds up to causal, guaranteed. So that's only because you have a surface integral. Okay? So any G0, that's going to be very important in our discussion on migration, both for conventional one-way and two-way, that statement. So well, I'm happy to move this and put math to that, but okay, so among the infinite set, so for wave, as it sits there, that's a wave prediction formula. A wave prediction formula in terms of surface values of the field in the derivative and information of rho inside. It says, if you want to predict a wave in a medium, you got to have some information inside, okay? Like velocity, like because that rho inside. If we go back, it needs alpha inside. In other words, it needs the velocity. Yes. Green's theorem says if you want to predict the wave field inside a volume, you need to know this whole thing's running on C0. In addition, you need alpha, which is the difference between the reference velocity and the actual. And if there's a source in there, it needs that A of omega. Whatever's inside, it needs to know it. And then this integral will fix up anything you messed up with that G0, plus gives you contributions due to sources outside. Because just because you write this way, the field inside a volume couldn't care less about your mathematics. You have a source, yes, and out comes a field. And it does something, and it produces something. We have these mass things inside the volume, outside all space. What the field is at a point doesn't care about what volumes you're talking about. The mass volumes, you follow? It's a physical meaning, it has a physical reality. So, among the, so this formula as it stands with any choice of G0 is a wave field prediction and belongs in the second part of the tutorial because wave prediction is part of what we need for migration, predict the experiment. Understood? Right now we're going to, this first tutorial has a different purpose. It's Wavefield separation. For Wavefield separation, we can't make any choice. Okay? Let me explain. So, is it clear? For Wavefield prediction, any G0 that satisfies this in the volume will work. Doesn't have to satisfy this in the outside the volume, but in the volume. There's infinite number of G0s. Understood? It's an inhomogeneous differential equation. Okay. So that's a prediction formula. To make a wave separation formula, why do we want wave separation? Separate the reference field from the reflection data. Separate ghosts from non-ghosts. Yes? Those are separation methods, yes? To separate the wave into different pieces, we make a choice here among the infinite possibilities of one. If you choose G0 there to be G0 causal, then you can compare this equation to the one that's valid for all R. This is valid for all R. But this one must have G0 plus. So if in that equation 8 you choose G0 to be G0 plus, then for R in the volume, you have, from the equation a few slides back, you have this. For any R, for every R, it's integral over all space. All space is integral on the volume plus integral of the whole world outside the volume. That's the integral of the whole world, yes? In the previous slide, you had P for only R in the volume. But for the field at a point in the volume, must be the field at that point R in the volume. So for R in the volume, which is part of anywhere, this plus this for R in the volume must be this plus this for R in the volume. Because the next slide was for everywhere. This is for some part of everywhere. What inside of the volume, this and the other equation must be equal. That makes this term here must be equal to this term. Clear? Because you have this plus a surface integral, this plus this volume integral. Yes? So that volume integral for R in the volume must be that surface integral. That's the basis of all the wave separation. This is a classic physics, chapter 7, Morse and Feshbach, page 100 of Born and Wolf optics. They call it the Extinction Theory because what this integral does, it gives you the contribution. This is the total field and the normal derivative on the measurement surface due to all the sources. The field is the field due to everything in the world that influences the field. And it says in this combination, in this sum, evaluated for a point R in the volume, you get the contribution to the total field at a point R in the volume due to sources outside. So that's the way Morse and Feshbach talk. The way Born and Wolf talk is, they call it the Extinction Theorem. They say, instead of saying that this is the contribution due to sources outside, they say it annihilates, it extinguishes the portion of the total field due to sources inside. It's the same thing, yes? In other words, the field in a point cares about sources everywhere, yes? To say it gives you the contribution to the sources outside means this filters out for a point R in the volume the portion of the field due to sources inside. They're the same. Okay? One's positive, one negative. So Ross Hill, Chevron, his thesis was involved in this kind of thing, in physics. So this is, all we're doing, bringing this to our interests. Yes? Yeah. Tim Keel, when we were at Oracle, we worked on this, finding the radiation pattern of the source. Okay, so the reference medium is arbitrary. Make anything you want. The only commitment you have is whatever you're describing the world has to be the world. Whatever you make the reference, then the lobe has to add the reference plus your sources must be reality. So if you change the reference, you change the what you consider sources. So for a certain application, for the application of separating the scatter wave or reflection data from the reference wave, we choose this. Okay? We choose in the marine case air and water as the reference, water all the way down. So then you say, what do I have to add to this to make reality? I have to add a source in the water, and I have to add earth. Those become two sources, yes? Two things you add to that reference to make the reality. So, and then the source is here, and then there's some cable here, and you have some kind of surface integral. So, if you made, and we will in a minute, a different choice, make the reference homogeneous, then you have to read. Let's say you made the world homogeneous, whole space of water, then air is a source. In other words, you have to change water on top into air. It becomes a term, and you have air guns and you have Earth. So with that choice of reference, which is what we choose for deghosting, yes? So there's two different, the only difference between separating the reference wave and reflection data and deghosting is the choice of reference. And the choice of reference determines how many sources you have. Okay? So that's, but after that, they're all based on this business. A surface integral. In other words, this doesn't tell you what the G0, what the reference is. It says some reference Green's function. These are the rows that you have to superimpose once you choose that. But whatever that reference and source combination are that makes reality, it satisfies that. That the surface integral, when evaluated inside that volume, gives you the contribution to the sources outside. What amazes me about that, that's an amazing statement. If you say the contribution of the field to the field, in other words, we can't be so jaundiced, so cold that we can't be impressed with what George brought. If you say, oh, this is the contribution to the sources inside, the sources outside, I understand. And if you say this, well, this looks like the contribution to the sources inside. The fact that this term will give you the contribution to the field in R inside the volume due to sources outside without knowing what those sources are, that's amazing to me. Whereas you do a surface integral and it tells you what sources of any variety that are outside contribute to the field inside without knowing what they are. Just need that information. Yes? Can't be too old not to be impressed with those guys brought. You know? That's a bad story. When you think about it, right? You don't need to know the sources. This surface integral tells you what sources that you don't know. This is not the field that those sources produce. This is the field that all the sources produce. That is the field on the surface. In other words, you didn't have to, you understand, separate. That does the separation. Okay. Well, you're in university. I can talk that way. Okay. So we have this, and then we choose this reference, and then, as I said, with that choice, you have two sources, and then you have to make, you have to say where is your surface and where is inside. So there's the reference Green's function with that choice of reference medium. If you choose your surface to be the cable and this, and evaluate it here, then you're getting that surface integral evaluated here gives you the contribution that the source outside does, contributes to the field at this point. Well, that gives you then what the air guns or whatever produce in the reference medium here, anywhere, in the water, in the earth, anywhere. Okay? That's why it's called Wavefield Separation. It's not filtering, it is predicting. Yes? Understood? So that's a separation between that produced the reference wave contribution at some point here, and you could produce it on the cable. So for example, and that's what Jing Wu will show, let's say you're going to do this on land. You have ground roll, part of a reference. You don't want to filter it and hurt your reflection data. You predict it. Yes? And so you predict it doesn't matter whether it's interfering. At this point, the reference wave is not the only wave. There's everything that's going on here. It predicts it. Okay? It doesn't try to filter it in the presence of other waves. Inside the Earth, the reference wave is not the only wave. Yes? Okay. So that's the point. So that will give you the reference wave. G0 means it's the wave that the source would do in the reference medium. You just evaluate that below the cable. If you evaluate it above the cable, you get the scattered wave, the reflection data. You get the contribution in the volume above due to sources outside that volume. Yes? So it's a way to separate. We have not used this in seismic. We ought to use it. We're using the deghosting one, but not this one. In other words, we have a reference wave in the marine, we have intersection along offset, yes? And we predict the data you paid for, yes? Predict it by evaluating this integral just on your table. Predict the reflection data. Yes? We have that acquisition. When Seacrest and I did this in 1990, you didn't have over-under dual sensor. So that was very interesting, and that's all. Now, the acquisition changed the whole world. This and the normal derivative, that's not a big deal anymore. Yes? We ought to stop cutting data we pay for along offset, even in marine. So this is not caught on as much as the deghosting. Exxon and others, they like the deghosting. But this for the wave separation is important too. So for the deghosting, as I mentioned, we have the Pioneer sitting here on DP. There you choose a different reference. You choose a reference of a whole space of water, and then you treat the air as you had to put a source here to turn water into air, some kind of alpha or something. And so you have source, source, source. That took a homogeneous world of water and turned it into air, air going to earth. 3 sources. Clear? Before there were 2. And then the way this works is you would take some surface integral, let's say down here, and you're at the deghosting. So let's say you're at this point R, and you want to know what the up field is. Yes? The upgoing field. Well, that's what it means on the receiver side to get deghosted. Yes? Understood? So this is the idea. If you, at this point, let's say you take your integral like this, you have 3 sources. You have air gun, and you have earth. The reference medium here is just this. Boom. Homogeneous, just out. So the air sends a wave out. The air gun sends a wave out. The earth sends a wave out. Everything is just some rho times this. Okay? So if you're at a point here, then the contribution, in other words, below the air gun, this R, then the air gun is having a wave down. The air has a wave down in that, with this kind of reference, and the earth is the only part of the wave here that's up with that G0 plus. Clear? Because everything is exploding in that picture. In other words, the picture here is that the wave comes from rho times those G's. Okay? The rho, the different rhos times this G. In that picture, everything just leaves the rho. So if I can determine the part of the wave at this point due to the earth, I have found the up wave. Let me repeat that. If I can find the portion of the wave at this point R due to the earth in this reference, yes? The earth being considered a rho, G0 plus, up, this down, air down, 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 up. The only source that's producing an up wave here is the earth at this point. We're evaluating below the source. So you take this cable, evaluate P grad G, G grad P, with the whole same form as before, evaluate it above, you get evaluated this way. Yes? So you get, at this point, the contribution due to the source outside. The only source outside is the Earth. And its direction is up. That's the ghosting. Yes? And then on the source side, you have to do a Green's theorem on top of Green's theorem, and I refer you to Jing-Fang's thesis. Okay? This has been applied by Jim Mahan on seam data and field data, Exxon and EGS. Okay? With good result. So this is the what I just said. The air, the wave from the air is down, the wave from the air guns is down, the wave from the Earth is up. So you get the Earth contribution by making that the guy outside. Close on top, the Earth is outside, the contribution of this business evaluated at a point above, as long as it's under the source, the evaluation point. And so what is the practical benefit? In other words, what did this bring to the world of deghosting? Deghosting is not new. Okay? Deghosting, if you think about it, is very simple. It's up-down separation. Yeah? A e to the ikz, b e to the minus ikz, right? Give me A and B, I get up and down separated. Yes? So it has to be very clear in a minute what this group, Jing-Fang and Mahan, have provided that you couldn't do before them. Let me make that clear in a second, yes? Because it matters for several projects. So this is a way to, if you didn't get the normal derivative, where if you had an isotropic source, you could predict the field and the normal derivative above. Let me not, you can read about that. But here's a practical thing. As I said, there's a very important issue here. You can't lose sight. You've gone all this Green's theorem, everything. Basically, you're trying to do up-down separation. Yes. If you give me two pieces of information at one level, P of 0, P prime of 0, I can get A and B. If I get A and B, those are up and down separated. Yes. Clear? I need two pieces of information to get A and B. I can give you two pieces at one depth or one piece at two depths. Yes, I can give you, but then in principle they're the same. In other words, you get A and B with this formula. Yes, you just solve two equations with two unknowns, and you get A and B. If you give somebody one piece of information at two depths, you get a different formula. With perfect data, they're equivalent. You get the same answer. If you have a notch in your data, this is going to be unstable. Okay? You understand? Where that gives you a 0. So if you have a notch in your data, this doesn't give you that problem. You understand? There's no sign, n pi, whatever, in the denominator. So if you're in what I'm saying is, if you have some kind of deghosting that depends on using the field on the cable and the free surface is 0, okay? That's great. You got two, but you better watch out for that notch. Yes. If you're in 6 meters of water, your streamer, and your notch is 125 hertz, and your data is less than that, you might not have an issue. Yes. If you're down at the ocean bottom and your first notch is 5 hertz, you better worry about it. Yes. You understand? So then you want to have two measurements at one level. Who's giving you two measurements at one level? George Green. The field and the derivative, yes? You understand? Okay. You get the point? This is what I just said. Depends on bandwidth, depth. So this is for the total theory for source and receiver deghosting. Again, I refer you to Jing-Fang's thesis. So here's an important point. What does this group provide? Let me show you the next slide. if you take this equation, and Fourier transform it over x, yes? That the fact that there's actually like x minus x prime and x prime is convolutional, so you get a product in the Fourier domain. You get this. This is standard typical deghosting. PVZ, they call it, yes? This is what industry does. This is what industry did before this, yes? Before us. So if you go, this is, yes? This is, and you apply that. And if they don't have exactly the normal derivative, they might need some factor, yes? Depending on the nature of the measurement. Understood? But, so, what is the benefit of this? First of all, to get to this formula, I needed a horizontal acquisition. I needed, my surface had to be flat to do a Fourier transform over that x. X is at a constant z, understood? In that integral. So to use this form, your cable has to be flat. If your cable is this, or if your ocean bottom is that, yes? And you use this, under those circumstances, we advocate do this. Get that topography, yes? That's the added value, right there. If you have a surface, yes? And you can describe what that measurement surface is, then use that, okay? Understood? Rather than, the other has an advantage. This has the advantage, it doesn't need to be a horizontal acquisition. Okay? So that's a differential of value. The other has a value over this. However, let's say I want to deghost my data. When Jim Mahan was interning at ExxonMobil, he kept saying we're going to deghost using this above. This R is in a volume above. And Exxon was all, they said, we don't want to deghost another cable. We like our data on that cable. We want that data deghost. To make this on the measurement surface, we figured out how to do it in this domain, but it has certain issues. This will not. Let me explain what the issues are. The Green's function that's sitting there is P. And the nature of its shape depends on how far above the measurement surface you're evaluating. Yes? And the closer you bring that output point to the cable, the narrower this gets. And at some point you don't have samples. Okay? In the Fourier form, you perform the Fourier transform. So you, in that process, you have assumed you had adequate sampling. Okay? So that's under the rug in the other case. So the summary is, if you have an interest in applying these methods of any variety for on the measurement surface, or I don't want to separate my reference and reflection data on some point here. I want to separate it in my data, yes? Then you have to do it in the Fourier domain. Okay? All the separation methods, ghost and so on. If you, yes, the other has it precludes you. Your sampling isn't good enough in the X omega to get you on the cable for this business. If the advantage of this is it will allow any shape. Yes? So if you're applying it to some onshore or ocean bottom or a cable that's not flat on purpose, yes? They sometimes make a cable that's not horizontal and use this. It doesn't care what the shape is, just saying what the shape is. Okay? So that's the value. For the work like with Dan and Nizar, where you need to be able to do effective deghosting, yes? The advantage, as you're going to see when Chalmar talks about the use of multiples, is we're saying that when you have a need for doing up-down separation in a very special way, yes, on the multiple, on the measured primary, that when you want to do that and your surface is not horizontal, think of that. So we're going to be delivering this as part of that use of multiple. business where there's an interest in wave separation of up and down of certain varieties, yes? Understood? Okay. Okay, I think that's it. You just said this. Roy's thanking you again, and I believe we've, Jing Wu is next.